Good evening, everybody. So let us start our lecture today, and today is September 30th, the last day of September in 2021. So today we will discuss red blood trees, one of the difficult topics in this course. So it is a little bit confusing and time consuming, and it needs attention to do. Okay, I will try my best to explain this. So in a previous week, we discussed with special cases of BST. That in a BST we normally expect a standard BST binary search tree, that is balanced binary search tree. But we saw some examples that if our data comes in different order, for instance, if you get 1 and the next value is 5, then it will go right side, right, BST, and the next value is 10, then it will go right side, and next value is 15, it will go right side, next value is 20, it will go right side, and the BST, this BST is growing in linearly, right? So in order to do a search operation, it will take log n time. It will take n time, big O n time. Okay. So, but we say that BST, we are expecting something like this, or pretty similar to this. That is height balance. So in this case, height will be h will be log Lg n with base 2, but in this case height is equal to n, right? So this is a problem for BST, and we saw that there are different kinds of trees. That, for instance, we discussed previously that AVL tree is a balanced, is a height balance. Actually, it's called a height balance on height balance BST. So that BST is a height balance tree, and we saw there are 4 different rules. Remember that we discussed 4 different rules for an AVL tree. So rule 1 as right rotation, and then rule 2 as left rotation, and then rule 3 as right left, and rule 4 as left right. 3 and 4 can be interchanged. So we saw the special situation that if we apply these rules in AVL tree rules, then a tree will not be growing like this way. It will be pretty height balanced. Okay, and today we will discuss red black trees. So a red black tree is a guaranteed height balance tree. It height balance a binary tree. Okay, like an AVL tree. While we develop an AVL tree, we use for some rules so that it becomes balanced itself by rotation. Okay, and similarly, a red black tree is a binary search tree. Okay, that will guarantee of height log n. So if height log n, if height is log n, then running time will be big O of log n. Okay, so the name infers that red black tree. That means that all of the nodes in a tree are either red or black color, nothing else. Either red or black color. So in our book, if we open our book, so chapter 13, red black trees. So here, this is an example of red black tree. Okay, there are some rules, 5 rules, 5 properties for a tree to be a red black tree. Okay, first of all, the root, this is called root, is always black. Okay, and the last one, let us go to last one. Last one is that for any path, if you go any path from starting from root to any direction, any path, this is leaf, and 3, then these are leaf. Okay, to go any direction, last one, I'm talking about last property, the number of black nodes is same. You see, when this direction 1 2 3, and you come this direction 1 2 3, 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 1 2 3, 1 2 3, always same number 3. There are 3 black nodes in all paths. If there is a violation in AN in a single case, then that is not a red blood tree. Okay. Okay. Then the second condition is a node is either red or black. So in this book, this gray color is red and black is black. Okay. What is the third condition? Okay. Third condition is that every leaf node, this is leaf, is black and nil. This is leaf because this is binary tree, right? Binary tree has 2 node, 2 children for each node, right? So this is nil. This is nil, this is nil, this is one child, so another child is nil. It does not have any child visible, so this is already nil and black. All nils are black. So since all nils are black, we can ignore this for now. We don't need to consider it. By default is black. We will consider. And then there are one more condition. If a node is red, then both of its children will be black. So here is red, then both children must be black. If it is red, then both children must be black. Not about grandchildren, immediate children we are talking about. Okay, and this is the most confusing point. The property, this is one. If a node is red, then both children are black. This is the most difficult property to maintain, and the last one also it is the number's second difficulty. Last one is that to maintain the number of black nodes same in all paths. Okay, but in order to make a tree a red black tree, we must maintain all of these properties. Okay, so number 4 is the most difficult one. Let us give focus on this. Okay, so can you please help me? Who can help me to read aloud this one? If a node is red, Adam, please read aloud this one.
Then both its children are black.
Okay, so what do you understand from this one? What does it infers in addition to this? So in addition to this, do you guess something else? Do you remember something else? So that it is straightforward that if a node is red, then all, but that's all, not all, both, only 2 children, right, will be black. But I'm telling that its opposite is not a restriction. If a node is black, then there is no such restriction. If a node is black, look at the black node. If a node is black, then it is not restriction that both children need to be either black or red. So that is a relaxation. Okay. That is not a condition, so we will use this feature. While developing, we will use that advantage. Okay, that means, so now let us recap what are the 5 properties. Who can tell us the 5 properties of a red black tree?
Either red or black.
Okay, all nodes are either red or black. Number 1.
The root is black.
Root is always black. Number 2, we got 2.
All the leaf nodes are black.
Yes. Number 3.
Red nodes, both of the childs of red nodes are black.
Yes. Number 4. That is the most difficult one to maintain. And
Any node that's nil is black.
what is the 5th one? What is the last one?
Any node that's like the nil and NIL is black.
No.
Number of nodes reaching to the farthest down is equal no matter
Yes.
where
The number of black nodes, not red node. We are not worried about number of red nodes. Number of black nodes in any path or all paths should be same number. If there are 10 black nodes in one path, all other paths will have 10 blacks. If there is only one black, then all will have one black. If there is 2, there are 2 blacks, no, then all paths will have 2 blacks. So, as the tree grows, right, and then the number of routes will be growing, then the more difficulty will be coming. Okay? So, now we will see how to build a red black tree. As if we are given a data set, okay, we will remember these 5 properties. Okay, we will remember these 5 properties. We will verify every time. We will verify these 5 properties. Okay, and then we have some additional rules we have to apply. So additional rules. First one, that in order to develop a red black tree. So the starting point will be the thing will be, we start with every newborn node will be red color. Every baby node is red color originally. We start with red. Then we will match all of the conditions with his father, grandfather, and top until top level to verify all of those 5 properties. Once those 5 properties are verified, then it will be a red black tree. But we will, newborn baby node is always red. But leaf is always black. Baby node always red. And remember that we will apply this, and if needed some rotation, we will apply the 4 rules of AVL tree rotation. We learned that 4 rules. And there are 2 more extra rotation, 2 more kinds of extra rotation. Okay. So read these slides or book. This kind of question will be for your quiz questions. Okay, I am not asking for the proof. A red black tree with n internal nodes has a height at most 2 log n plus 1. Okay, so you may get that. What is that called? Proof. I am not asking for proof. Okay, I asked you to understand how this happened, and actually we need to understand what did you leave? Rotations. There are 2 rotations, so we need to go 2. What is that? Okay, there are 2, and in addition to the 4 rotations we discussed, right, AVL tree. In addition to those 4 rotations, there are 2 more additional rotations. Okay, for in order to develop a red blood tree. So let us understand these two rotations. Everybody please give attention here. Look at my skin. It is a critical thing, okay? If you understand this, then it will be easy, many things. So for instance, this is a tree. So remember that for AVL tree we rotate with only individual node, but here we are rotating branch a branch of a tree we are rotating, and here every time we rotate, since this is a BST, we need to maintain Bst properties as well. So what is the Bst property? Every node has two children, and the value in the left child is less than the parent, right? And the value in the right child is greater than the parent for all nodes, right? So in that case, if alpha is the left child of X and beta is the left child of Y and gamma is the right child of Y, in that case alpha is less than beta and beta is less than gamma, right? Thus alpha is less than gamma, right? Gamma is the highest value. And okay, so we need to understand rotation. Rotations means it is not the like rotation that we discuss in AVL tree. It was easy. For instance, for AVL, like right, we did quickly left rotation, right? And we made a balance. For instance, there happened, for instance, this came here. For instance, A, B, and C, then A came here. So left rotation and then K came here. So this rotation is not like this simple, because it will be rotating with a branch. So how this rotation? Please let us understand. Think about that. For instance, is called right rotation, or this is called left rotation. Left rotation means, you see that this symbol means, for instance, think about that this is a ball or piece of paper, and this is a string. So this is hanging, this branch is hanging here, maybe hanging on the roof or on a bar. So now it is balanced, hanging in a balanced way, right? But for instance, if we want to rotate this one, rotate this one. So you're going to rotate, then what will happen? This will be going down, right? If you do left rotation, then X will go down. Okay, and then we want to hang upon Y. Instead of X, we want to hang upon Y point. So it will no longer be hanging here. So it will be hanging, I want to hang it here upon Y. So the first condition is that for left rotation, the right child of X must not be null. So if there is no right child of X, then how can we hang? Right? In order to hang on Y, X must have right child, right? So this is the first condition. So okay, the first condition is that the right child of X, that is Y, is not null. If it is null, then we cannot hang. You understand? If there is no Y, then we cannot hang on Y. So give focus if you understand this. And if you do not understand this, then when you go home, take some string and take some papers or this round papers and make hole, and then put number, okay, and then put glue or something and try to hang this way, then you'll understand. So but give attention that. So what we want to do, we want to hang this tree based on its branch, on this branch. This one, for originally, let us think that this one origin, the main branch. But we want to hang that. Now we don't want to hang on the main branch. We want to hang on the another branch, sub branch. So then it will happen. So then what will happen? You see that, remember that if you hang this one, right? So then it will be fixed, it's okay, alpha is okay. And then so y will be your root, here y will be your root hanging point. Then this one x and y, this true string will be joining, right? Or joining, not joining, actually there will be some, then y will have 3. If you do not join, then y will have 3 children. One side is x, another side is beta, another side is gamma. So isn't that a violation of BST? Yes.
What?
BST is a violation of BST, right? A BST has always 2 children. So if you hang on directly here y, then y will have 3. You see that x, beta and gamma, 3 children. But it cannot have 3 children. A BST cannot have 3 children. So this is violation, right? So we need to maintain. How can we maintain that? So that we need to merge this and this together. So that merging is a little bit challenge to understand. On the right side, you see that merging. It is going on over here. So it is hanging through I. And then if you follow my technique, how do we do it? So for instance, we know that, as it says, alpha is always less than beta, right? And beta is less than, always less than gamma. And gamma will go as is. So gamma will go on right side. Okay? And alpha is less than x. So alpha will be always left side of x. So alpha is as is. Right? So then only position beta. Only you have to position beta. And beta is greater than alpha. So beta will go in the right side of x. Because whenever it comes over here, so that in ABLT I showed a technique for this, right and then left. What do you do? Fulfill a triangle, right? I said, right? The technique is make a triangle. So here, same, make the triangle. Make the triangle. Then you need to send then cut off this, and cut off this. Okay, sorry. Don't cut this. It will stay as is. So here, just cut off this, disconnect this, and then beta will go with x. And how do you remember that? As I said that this gamma is stable, so make it stable on the right side, and alpha is stable. Okay, the problem with beta, so who are stable, put them first, and then since this will be hanging, so then this x will come with y, and then it shows that there are x has one hand left, and that position beta will go that position. This is the technique, but for small branch it is intuitive and then it is easy to remember. If you follow this, that you will see that maybe there will be large branch that we need to rotate. Sometimes we will rotate large branch, not like simple like this, but same technique. Okay, everybody understand this? Does anyone has any question? Okay, if you don't feel shy, okay, please let me know if you don't understand this. Still, if you don't understand this, then what I like you to do, go home and maybe you can cut some piece of papers, okay, and then put glue, okay, and then make a hole and then put some string First one make like this and then try to hang on later on y. Then you will see the problem with it. Problem will come with this thing. Okay, so then we need, so that how this problem will be solved, we need to break this line and we need to put it here. Then problem is solved. This is called left rotation. For left rotation, you know, to left rotation, what is the first condition? That the right child of x must not be null. If it is null, then how can we rotate, right? You cannot rotate. Where is the trick? This is called left rotation. Everybody is okay? Then there is another kind of rotation. It is called, you see that, so left rotation sometime it will happen on a large branch, not a simple that one. For instance, let us understand this one. So we want to make a rotation upon x and y. So it is, now it is hanging on x. X is the root, right? We want to make y as a root. Okay, so the first condition is that we need to verify that the x right child of x is not null. Yes, it's not null. Then it's doable. Then how we will do that? So for instance, first of all, the technique is that first of all, keep this aside as is, this one. It is not a problematic. Problematic is that this is alpha and this one is beta, right? And we saw that this one is gamma, right? So we saw that. So then it is good that, for instance, this is gamma, maybe this is gamma right side, and this is maybe beta right. So forget about this. So these are not problematic. So but one thing is that these will stay together and this one will stay together. So consider that this is alpha dash, and this is beta dash, and so this is gamma dash and beta dash. That all together, this will come all together. Okay, do not throw this. So any children or any branch from beta, do not throw this. Keep, it will go together, and any subsequent part from gamma will go together. Do not throw this. Then what we will do? We will be hanging here, right? We will be hanging here. That means it will be root. So then 18 will come over here as a root. So you see that 18 come as root, right? And then this 10, this 11 will be coming here as a left child of 18, right, of y. Then it will bring with, this will bring with alpha. So this will bring with alpha, this is alpha, right? And this is gamma. As we said that, those are the obvious, put them first. And then this part is beta, right? Beta will go the right child of x. So this part is beta. This part is beta. And then this one, I said this one will be as is. Don't touch that one. You understand? A little bit complicated, right?
Yeah, I'm good.
The technique is that first of all we need to check for left rotation. We need to check whether there is right child on who will be rotating, right? If there is no right child, then exit. We don't need to rotate. We cannot rotate. And then my technique is that figure out alpha, beta and gamma. Then for the left rotation, alpha and gamma are fine. Problem is beta, and beta will be go to right side of x, right side of alpha. This is called left rotation, and if you understand left rotation, then there is another rotation is called right rotation. Right rotation is just opposite of left rotation. So for instance, we have this branch like this, and we want to do a right rotation here. So in the right rotation, that means we want to hang on this one based on x. So this will be our hanging point. So based on x, this will be our new hanging point. So now if we hang this one, right, the problem will make here that it will get 3 1 2 3 child BST violation, property violation. Then we need to do something what? So we said alpha, right? This is alpha and this is beta, this is gamma, and same thing, alpha is less than beta and beta is less than gamma. Okay, and here so this part here, and this part will be hanging part. This part actually will come here. So this part will come here, and then this part has a right child is gamma, and left side was empty. So this beta will come here. So I would like to say, understand the left rotation first, then it is easy. Right rotation. Okay, now what are the new things we come up with today? In a BST, in a red black tree is a BST, right? And it has 5 properties. Okay, so let us recall the 5 properties again one more time. Root is always black. What else?
All paths have the same number of black nodes.
Starting from root to any leaf, all paths have same number of black nodes, right? We are not concerned about red node. Okay, that is the last one. What is the number 2?
Both children of a red node must be black.
That is number 4. Okay, you got number 4. If a parent is red, then both children will be black. What is the number 2?
Every leaf is black.
Yes, all leaves will have nil value and color will be black. Okay, and what is the number 3?
All the leaves are black.
Oh, that is 3. Or number 2 is missing. No, that is 1.
One that all the reds are, or all the nodes are either red or black?
Yes, all nodes are either red or black, nothing else. It cannot be white. Okay, so now and then we know 2 kinds of rotations, right? Those 5 properties and 2 kinds of rotation, left rotation and right rotations, and there are 4 additional rotations we learned from ability, right? That means 5 plus 4, 9, and these 2, 11. So there are 11 things we need to consider while developing a red black tree. So this is sometimes is difficult, and it is okay. So book, read the book, please. The book has algorithm for left and right rotations. So this P means here parent. Okay, so please read this and try to understand the rotation. And I explain the movement fact. Okay, algorithm is here. So in this algorithm, what will be running time for this algorithm? in terms of input.
If I remember reading in the book, it was 2 LG10.
Maybe constant.
No, rotation is constant, but for the entire algorithm, it is what is that called? Binary search. There are coordinates both. I'm trying to say that there is no loop here. Okay, there is no loop over here, and it says constant, but in my understanding, if you start from the beginning and go all up, you have large branch, then maximum it can go log 2n. But book says rotation is run on big on time because it does not have any looping. One thing is that. Okay, so now what we're gonna do? So okay, so oh, book has this one, right? Okay. Okay. So let us start today and give attention, please. We will spend 20 minutes to understand how the insertion or how to build a red black tree. Okay, and building a red black tree, I said that we found that there are 11 rules, right? You need to remember. So it is not much easy like other things that we've discussed so far. Okay, so our goal is to start a build a red black tree, and then one more thing that I told that there's one more property. We will start while starting a red black tree. We will start a node, and every node will be by bond will be which color? Red color. We will start from there. Okay, so let me give I will upload this one. Okay, so I got this from internet, but I found there are some problems. I will fix this and then I will upload it in video. Then okay, for instance, we are given this data set. We are given this data set, a sample 1 to 10 numeric numbers. We want to draw a red black tree. So initially we got number 1, and then the number 1 will be red. By bond, right? Then we will check whether is there any previous node, existing node. If it is not, then this is the only root, right? And this is the root node, and a root node always black. So then we will recolor. So this is root, so recolor. So recolor means make a different color. Since only red and black, so recoloring means if it is black, then make red. If it is red, then make black. Nothing else. You understand? And then exit. If it is only one node, the first node we get initially, we will make it black, and we will check the second thing. Then we will check whether it is the root node. If it is yes, since we see that there is no existing node, right? This is root, so then make it black. Make it black. Then done, right? So then at this phase, what is our red black tree? Is a black root with 1. Does it maintain red black tree properties? Let us see. First of all, root is black is okay, number property 1 is okay, right? And every number 2, every node is either red or black is okay, 2 number is okay, and it has leaf, so nil, we are not considering this. By default we think that is okay. So this is property. And number of red node in this path is 1 and this path is 1, right? So all 5 properties are maintained, and it is also BST, right? Okay, now if we encounter number 2, so then we have 1 over here, and when we encounter number 2, how we will start? So the 2 will go to the right side of 1, right? 2 is greater than 1, so since it is a BST, this 2 will go right side of 1, this 2 will come over here. Okay, initially it will be red. Okay, now we will check all other properties. What is the first property? Is the root is black, it is maintained. Okay, what is the second property? Huh?
Either red or black?
Yeah, red or black, it is maintained. What is the third one? We will see is there any violation or not.
All the leaves are red or black.
All?
That's the.
Yeah, it's okay. That one is we will no longer draw this. All the leaves, okay? Let us forget about leaves because all the leaves are okay. And then what is another one? So then it's okay, right? Or everything is okay. There's all condition met, right? All condition met. Now let us get another number 3. Okay, so this here. Another number 3. So we got another number 3. Okay, so then we will start 3 will go the right side of 2, right? This is the step 1. This is initial step 1. But after first step we will count all properties. Okay, initially it will be red, right? Initially this is red. Okay, now what we will do? Check. Root is fine, right? Okay, the problem is that this parent is red, so we said that if a parent is red, then
Children are black.
must be black, right? So this one in step 2, we need to go step 2. We need to recolor. We need to recolor this one. Okay, recolor means it was red, we made it black, right? We are not concerned about at this point not the parent, only the new node. Okay, step 2, recolor. Okay, then let us see, is the number of that, or is that condition, last condition, are the number of black nodes in all routes same? So the left route, it has empty, right? This is 1, this is empty, this is leaf. This is only one block. And the right side has how many? 2, right? So the fifth property is violated here. Adam, got it? You got it? The fifth property is violated, right? So that means in this side and the right side, there are 2 black nodes. On the left side, so if you even consider one over here, if you consider one over here, leave whatever you say, is that this side has 2 and this side has 1. Don't be misled. This side has the left number of nodes, black node is 1, the left children, okay? Because we have to consider this way, okay? And so it's 3, 2, okay? Then we need to do a rotation. So what kind of rotation we need? We have right and right. So we know that from ABL tree, if there is a right rotation, then what do you need to do? Rotate left. Okay, this rotate left. So if you make, for instance, 1, 2, 3 and rotate left, what will happen? This 1 will come here, right? That happened over here. Okay, so that is happening over here without changing any color. So this is our step 3. This is my step 3. And now what we will check? Okay, we will check again all of the conditions, right? So here, which way you go? From top to bottom. Number 1, then the root must be black. So then last one, we recolor the root. So this is our step 4. What do you do? Recolor, right? We recolor this, we recolor this, recolor root, we recolor root. Now it is a red black tree, although there is no red. So that means it is not a condition that a red black tree must have a red node, right? If it is only one node, then it's black, then true, and we saw that there are 3 nodes, but still there is no red. So this is why sometimes I thought, how it became a red black tree? Rather I would say it's black red tree. Okay. Because it has already, it must have a black. Okay, but people say red black, I will say red black. So everybody understand this? Do we need to recap or it's okay? It's good? Okay. Now this is our original red black tree. Okay, now we will go to the next one. Next one, we are facing next number. 4. Okay, so I got this slide from internet, but if I would make it. This is black. I would make the color actual red, original color. this is black. Okay, and then when it comes number 4, we will start it as a black, right? All new baby nodes are red, right? We will start it as a red. Now we will check all properties, all 5 properties. Is the root black? Yes. Okay. Are the number of red black nodes same? Yes, 2, right? This side is 2 and this side is 2. Okay. All are red and black. This is 4. And the problematic one is which one? I said number 4. Right? If a node is red, then all nodes must be black. Okay, so then red, and it has 2 labels by default black. So then now it is okay, right? We don't need to do anything for this one. Now are you okay for this one? It is simple, right? This one, because it doesn't make any problem. Okay. Now when we encounter 5, so let me go back to this one. Originally this was red, and then 5 will come with red, right? And since 5 is the right side of greater than 4, so it will go right side. You understand? As a BST, it will not come. So now what is the which property is violated?
Five's not black.
Huh?
The node 5 isn't black.
Yes. So since 4 is red, okay, then 5 needs to be black. So let me select. Originally this is like this, this, group, right? Group. Okay. Okay. So then let us think that this is our first. So then what do we need to do? First one, then we got this one. Then we need to recolor 5 first, right? Okay. Does it turn in the next step? Let me go to the second. Trying to fit it here. Okay. The second one will be, steps 2 will be recolor. So this one was step 1. This one was step 1, and this one is step 2. Recolor 5, not 5. Now one problem is solved, but is there another problem? Yes, right? What is the problem?
The number of blacks on the left side is not.
This new problem arises, right? The number of black nodes on the right side is 3, right part, and the left path is 2, right? So this path has number of black nodes is 1 and 2, and this side is 1, 2 and 3. Okay, so then where the violation arises? Violation arises here at this point, right? Violation arises this point. So then this is right, and then again right. So remember that AVL3 rotation, for right to right we need to do a left rotation, right? Okay, so the next step is to do a left rotation. So we will do a left rotation, then it will happen that a 4 will be root with color as is, and then 3 will be coming left side of 4. You understand? Joining will be here. So the next slide has that information. So here three is this is not correct. How can I select all together? Group. This is step 3. So it comes from the previous side. So 4 was red and 3 and 5 was black. 4 was red and 5 and 3 were black, right? In the previous black. Four was red, 5 and 3 was black. Okay. Now let us check all condition again. Parent is black. Okay. If is a root is red, then all nodes are black. Children black. Then 3 is black, and then 5 is black. Right? And number of black nodes in the right side is 1, 2, and this way is 1, 2, and this way is 1, 2. Okay, so all conditions are met. So this is an red blood tree. Okay, so it is okay. So this is our step 3. Could we take this in previous space? I will take this in previous space. Space is over here. So here, this is our step 1. Now let me recap. This is step 1. This is step 2. What did you do in step 2? We recolor 5, right? Step 1 we just inserted new node 5, and in step 2 we just recolor 5. Recolor 5, And what did we do here? In step 3, this is step 3. What did we do here? Rotate 3 to 5. 3, 4 and 5 we rotate, right? And then is okay. Now it is okay. So anyone has any question? You see that it is growing and it is growing, and then complexity is coming more, right? Yes.
This isn't directly related to this example, but I'm wondering if you insert the same elements into a red-black tree, but in a different order, can that change the color of the nodes?
You cannot do insert same element in a red-black tree, because red-black tree is a binary search tree.
Well,
In a binary search tree, cannot have duplicate element.
I'm not saying they'll be in the tree in a different order. I'm saying, like, rather than inserting 1, 2, 3, 4, you insert 3, 2,
Yeah,
4,
that will
5,
happen. We'll see another
1.
example.
Okay.
Same thing. Always. So if it is inserting, for instance, here, now we insert another number, then either come into the left side or right side. Right? So in this case, we are getting right side because the number is coming in alphabetic, in numeric order. It comes in different order. That's no problem. We always maintain. For instance, this could be 15. Right? This could be 15. So if it is 15, then what happened? The same, right? In this case, same, right? So then 4, 15, right? If the next number comes 10. So here in this example, it has the next number 6. So in that case, next number is come even 6. Then 6 will go where? In the left side of 15, right? That was your question?
No. Because what I'm wondering isn't the order they'll be in the tree. What I'm wondering is, can the colors of the nodes change depending on the order you insert them in?
Maybe.
Okay.
Yeah, maybe. Because for instance, if we get, let us think that if we get another element 6 after that, we have 6, right? But if this 5 was not, 5 was 15, right? Then the 6 is red, right? So then you have a path like this way. You have to consider the number of black in this path, and number of black this path, number of black this path. So that maybe needs to recolor, may come different order. We will have some examples. We have many examples. This one is straightforward, so I'll come up with this straightforward one. So because this is complicated one, we need to understand. If you understand this simple thing, you will be able to do this complicated. Okay. And you see 6 is growing and 7 is growing like this way, and then at that time it is going to like this way, it is rearranging, and then finally you see that after this, when 8 comes in here but here, then it will be more problem. You see that this tree become, you see that then here origin was 2, right? Root was 2, but at this point even root become 4. Okay, so I see, let me see if there is another example. Okay, delete is more critical. It has 6, 6, 6, 6. Different conditions, but talking about this one, right? So your question is that if we encounter first value 26, then next value 17, Okay, then another value 41, then maybe 47, then maybe 30, right? If it comes in different order, so then yeah, it will be, you will have, it may have different color, but it will be, in order to be a red black tree, it will maintain all 5 properties. When the book has examples, and if you do Google search, there are a lot of red black tree examples. You can try with this, but I would recommend to start with the simple one. So we counted that 11, there are 11 or 12 rules, right? We have to follow in order to make a tree. So that's now for today, tonight. So the next thing, I will upload this in D12, but there are some problems, there are some issues in color. So this slide I got online, but they are not exactly color because I did not go through all. As I go through all, then I thought I would fix it. But here, so instead of red, they put maybe green. That's red on is green, considered as green. Okay. And I will upload this and then do it. So let us get the attendance. And does anyone has any question? Okay, that's good. So now let us get